Hi everyone, thank you very much for joining our webinar on advances in geotechnical engineering from lab and field testing to seismic risk assessment. I am Maria Liapopoulou. I am the second Young Members Subcommittee Chair, and we have with us today Dimitris Pitilakis, Anastasios Kapouniaris, Stefania Apostolaki, and Chiara Amendola. Having graduated from the Aristotle University of Thessaloniki, it is great to have you guys today, and thank you very much for accepting the invitation. Let me just make sure that this is full screen. Okay. So before we begin, I would like to ask the audience to keep your video cameras off and your microphones on mute during the presentations. We will have time for questions at the end, and if you have any question in the meantime, please type them in the chat. And also note that the seminar is recorded and will be uploaded on our second YouTube channel. So by agreeing to be part of this event, you agree that any information or views you share will be made public. Our second fund is open for applications. With an award of up to £1,500. This scheme is open to second members, and it can be used for activities related to engineering dynamics, including lab and field testing, development of new tools or software, attending or organizing site visits, field trips, workshops, or post-disaster missions, among others. So if you're interested in applying, please visit our website, which is given at the bottom of the slide, and the application deadline is at the end of the month. We will have 3 vacancies open for our Young Member Subcommittee, and we will make an announcement in September. If you're interested in joining the committee, you will need someone with a valid second membership to nominate you, and you would need to be a student second member of any age or an individual or corporate second member under 35. So keep an eye on emails and the LinkedIn page for the announcement of this. And earlier in the previous month, we had a site visit to the Schofield Center. Many thanks to everyone that joined, and many thanks also to Professor Madabusi for guiding us in the centrifuge beam facility and presenting on the principles of centrifuge modeling, as well as to Sulak Nawarasiya, Diarmid Shu, Carlos Espanyol, and Nicholas Lee for guiding us in the center and presenting their research. Now back to our speakers for today. Dimitris Pitilakis is a full professor in geotechnical earthquake engineering at the Aristotle University of Thessaloniki, specializing in soil foundation structure interaction, dynamics of foundations, and performance-based design. He has published more than 150 papers in scientific journals and conference proceedings, and he is a member of national and international earthquake engineering societies. He is a reviewer also of international journals, and he is in charge of the shaking table facility of the Aristotle University of Thessaloniki and the field scale Europroteas facility. Anastasios or Tassos Kapouniaris holds an MN's degree in civil engineering from the Aristotle University of Thessaloniki and a master's degree on the sustainable development of structures against earthquakes and other natural hazards from the same university. He is currently undertaking his PhD on dynamic properties of soil rubber mixtures, and he's working on various research projects in geotechnical earthquake engineering, both in the lab and in the field. Stefania Apostolaki is a PhD student and researcher at the Aristotle University. She holds an MN's degree in civil engineering from the University of Thessaly and a master's degree in earthquake engineering from the Aristotle University of Thessaloniki. Her PhD is on the seismic hazard and risk of infrastructure and is funded through a scholarship from the Hellenic Foundation of Research and Infrastructure. She's participating in various research projects, and she has published 4 papers in international journals, along with 19 contributions in national and international conferences. Chiara Amendola is a postdoctoral research fellow. She has graduated with honors from the University of Napoli Federico II, with her master's thesis receiving the Best Master's Thesis Award. She holds also a PhD from the Aristotle University of Thessaloniki, funded by a Marie Curie Fellowship. And she's currently working on several research projects specializing on the seismic vulnerability and risk assessment, soil structure interaction, and the seismic behavior of existing buildings. So without further delay, I will now hand over to Dimitris to start the presentation.
Thank you, Maria. Let me switch. All right, now you should be able to see my full screen, right?
Yes, great. We can see that.
Thanks, Maria, for this presentation. It is always a great pleasure for us professors to collaborate with former students and see their advances. So I'm really happy for you. And I'm really glad to participate to this webinar. My name is Dimitris Pitilakis, as Maria told you, and I will briefly discuss the title, which is Advances in Geotechnical Engineering from Lab and Field Testing to Seismic Risk Assessment, highlighting essentially the work that we are doing in our laboratory. So basically, I will briefly discuss many subjects, and then Tassos, Stefania, and Chiara will dig into more details in their respective presentations. So, what are the main research fields that we are working here in Thessaloniki? Thessaloniki is the second largest city of Greece. It is in the north of Greece. And we have a laboratory here, which is called the Laboratory of Solid Dynamics and Geotechnical Earthquake Engineering. So basically, we started from maybe 30 to 40 years ago by doing simple solid dynamics and geotechnics, anything that really has to do with this. And then since then, we have been working on geotechnical earthquake engineering in general, engineering seismology, and recently, in the last 15 years, we also switched to seismic hazard, vulnerability, and risk assessment of buildings and infrastructure, soil structure interaction, lifelines, seismic design and retrofit of monuments. So basically, we are covering a very vast, let's say, engineering field, always with a focus on geotechnical earthquake engineering. So just to briefly highlight and mention a few things about our laboratory testing facility, Tassos will talk later on with more details on what we are doing. So basically, we are equipped with state-of-the-art laboratory apparatuses. We perform routine determination of physical, mechanical, and dynamic soil properties and high-quality research in soils. Soil classification, testing of soil samples, evaluation of dynamic properties, evaluation of liquefaction potential, and a small scale shaking table that we are currently using. But again, as I said, Tassos Kapouniaris will talk about this more. Then we have a big natural laboratory, as we say, where we do many kinds of field testing. So basically, the natural laboratory, as we call it, it is outside of Thessaloniki, at the very exact epicentral position of a big earthquake that happened almost 40 years ago in Thessaloniki, 45 years ago in Thessaloniki, in 1978. This place is called Eurosize Test, and it provides an instrumented site to perform multidisciplinary studies in soil dynamics, earthquake engineering, engineering seismology, site effects, wave propagation effects. So it's fully instrumented. Imagine that it is the longest running instrumented array in the world because it has a continuous operation since the early 90s. And it is instrumented with approximately 25 instruments in three directions, north, south, east, west, and we are recording earthquakes down to the bedrock, which is in this valley. It is at almost 200 meters. Then all these data, let's say, is used as a basic input for research towards seismic risk assessment and mitigation. So it input models. It is a valley which is very well known because we studied it for the last 30, 35 years. So we know the exact 3D geometry. And it produces a unique database of high quality seismic records. We are continuously recording since the early 90s earthquakes. Recently, when I say recently, it is almost 15 years ago, we constructed this structure, which we call the Europroteas, because it is the first structure of its kind in Europe to study soil foundation structure interaction and wave propagation in real scale. So it's a steel structure that supports reinforced concrete slabs. This is the strong motion database that we have in our lab, and it records all the earthquake records it records all the earthquakes that take place since the early 90s. It is open to the public, so anyone can browse and download earthquake recordings, small earthquake recordings so far, but if we are lucky, we are going to record also a major one. Now, another big aspect that we have been working on is the field monitoring that we principally do in this Eurosize test valley. So we are doing 2D and 3D geological and geophysical models with extreme detail, as you can see here to the right. Anything with geophysical tests, surface accelerometers, and downhole arrays down to the bedrock. Then another aspect of our research focuses on microzonation studies. We have performed microzonation studies, if I'm not mistaken, in more than 6 or 7 cities in Europe. And we can get results or data that looks something like that. So this is, let's say, the spectral acceleration. This is Thessaloniki. This is actually the port of Thessaloniki. So this is the spectral acceleration as output from a microzonation study for a certain earthquake scenario. This is the spectral acceleration for a period of 0.6 seconds. These are all useful information for big projects like the construction of the metro line, the underground, the subway line, which passed somewhere over here. And then they used our results in order to seismically design the tunnels and the stations. Then moving forward, lately we have been working on a lot on seismic vulnerability assessment. So we deal with cities. This is again the city of Thessaloniki, where for an indicative earthquake scenario, we have the damages in 5,000 buildings. Some of them are green, yellow, and red. This is traditional marking depending on the damages. And again, here we can see an aggregated distribution based on the municipalities of Thessaloniki. You can see that, for example, these 26,000 buildings, most of them, 2/3 of them, are going to be yellow. So they are going to have a slight to moderate damages. Then we expanded our research to the seismic vulnerability of networks. This is important because, for example, if everything is interconnected, so this is the road network of Thessaloniki, this is the bridge network of Thessaloniki, and we are starting to see what's going to happen, for example, in the road network if a bridge here to the, let's say, to the south of Thessaloniki have important damages. Actually, this bridge here, with this, where you see the laser pointer, is a bridge that connects the airport to the main road. So basically, in a, let's say, given scenario of an earthquake, this bridge will be damaged, and this means that there is not going to be immediate access to the airport. So this is important. Then we are studying systemic vulnerability. What is systemic vulnerability? It has to do with all kinds of lifelines. So basically, there is systemic intra and connected, intra and interdependent systems. This means that, for example, when the water system, if there is an electricity breakdown because of an earthquake, then probably a pumping station. Here is the water network, right? So probably a pumping station is not going to work, which means that if there is a fire because of natural gas somewhere in the city, maybe inside the pipelines there is no water in order to put out the fire. So this means that all the systems are somehow interconnected, and we have been studying with this. We have been studying this for the last 6 or 7 years. Then another aspect of our research focuses on seismic zonation. Stefania will talk more about this. So depending on the region that we study, this is the whole of Greece, we are proposing updated earthquake maps, earthquake hazard maps, zonation maps, in order for the engineers to be able to design the structures in order to resist earthquakes with as accurate representation of the hazard as possible. But Stefania will talk more about this next. Then another branch of our research is the geotechnical seismic isolation. This is a very low-cost isolation that essentially focuses on intervening at the soil beneath the foundation or around the foundation. And we have been doing large-scale testing in Europroteas and Eurosize test. Basically, we can see that here we are using gravel and rubberized tires, recycled tires, and we created a layer below the foundation. You can see here, this is more black than the gravel only on top. And then we placed the structure, we placed Europrotea structure on top, and we produced a shaking and recorded what's happening. The response. Here we did the same with EPS, expanded polystyrene, below the foundation. What we have recorded in our field scale tests is that basically if you use, in this case, a mixture of composed of 70% per weight gravel and 30% per weight rubber, this is in volume around 50-50, you can see here that the red line, regardless of, let's say, the excitation frequency that you can see here on top, remains the same. What does not remain the same is the gravel-only mixture, let's say, and another mixture having a lower proportion of gravel. So basically, we can see that using this kind of geotechnical seismic isolation, there is a reduction of 40 to 60% in the actual response, which means a reduction in the earthquake, let's say, shear and moment forces that are transmitted to the foundation. Then another thing that we've been lately working on is the seismic risk assessment of schools and hospitals. Schools and hospitals are critical infrastructures. So basically we created an online platform to be used in schools, and later on it can be populated for hospital buildings, where we can do basically a seismic risk classification of the building and have immediately the vulnerability of such critical infrastructures. Here you can see, for example, that we have applied this to the Central Macedonia. This is the prefecture of Central Macedonia. It is something like 2,300 schools, and for a given hazard, let's say, regional hazard, we can see immediately, based on some, let's say this is a scenario with a return period of 475 years, we can see that depending on the material and the lateral load resisting system that one inputs, we can have immediately the risk or the vulnerability, if you like, of each one of these schools. And then, for example, this is very important for the prefecture, because then they can immediately go and assess, for example, the red buildings that need retrofitting or whatever the stakeholders actually think it's best to do. Another thing that we have been working on is the urban scale risk assessment. Chiara is going to talk more about this. So basically, we've extended our vulnerability and risk assessment from a single structure to a city or a region. And this we do it by including also soil structure interaction, so the presence of the soil. This, as you will see in Chiara's presentation, changes a lot. And again, this is the basic, the principal city of Thessaloniki, I'd say, so we can have aggregated the vulnerability and the risk of each one of these typologies of buildings. What is the level of the expected damages? Now, just in short, right now our laboratory is involved in 4 big European projects with a total budget of 2 million euros, maybe more than 2 million euros. And as a very conservative estimate, we have participated in more than 30 European projects, mostly European projects, national also, with a total budget of more than 10 million euros in research targeted towards geotechnical earthquake engineering and risk assessment. And with this, I would like to thank you. Here I have some links, or basically you can just scan this QR code and it will direct you to our dedicated website where you can find all this presentation. Thank you very much for this. Should I stop sharing?
Thank you very much, Dimitris. Tassos, you can start with your presentation.
Okay, I will start sharing my screen right now. Is it okay?
Yes, great.
Okay. First of all, I am Kapouniaris. I'm a civil engineer here in Thessaloniki, in Aristotle University. I want to personally thank Maria for the invitation, and I'm very grateful for her approach here. Since we studied together when she was back here in Greece. So I'm gonna talk you mostly about laboratory experiments, as you see in the title. And as Dimitris said, our research unit deals with many of different types of research work. So here in our research unit, we deal with large-scale experiments, in situ testing, all this risk assessment, and of course, my work is focused mostly on the laboratory testing, as you see here in this red. Now, our lab has an area of more than 450 square meters. This is a video of our equipment and our facilities here in Thessaloniki, and members of our staff and our devices. Our work in geotechnical engineering firstly deals with soil mechanics. We have many equipment for direct shear testing, for rig shear testing, for unconfined compression tests, for the classification of the soils and the estimation of physical properties. And of course, our work also contains dynamic testing of soils and rocks, for soil specimens and rock specimens. We have 2 different cyclic triaxial devices. We have resonant column devices. We have 1 small shake table, as Dimitris said. Of course, Bender element tests, and I will be more specific in the next slides with details. The video now stops. This is our facilities like with a quick video. So now let's go to our first device, which is the resonant column. As you see here in the picture, I will also turn the laser on. Just a moment. Yes. This is the main frame of the device. This is the triaxial cell where the soil sample is input here. This is the cell pressure table where we can change the confined pressure of the material. And this here is the electronic equipment when we can adjust the function of the devices and actually make the estimations that I'm gonna talk to you about later. So This device has the ability to work in both torsional and longitudinal excitation. As you see here in this picture, this is a soil sample. We have fixed the base, and on the bottom, we can apply either a torque, like a sinusoidal torque, a harmonic torque, or of course a longitudinal force. In that way, as I can show you in the next slide, we are able to measure the deduction curves of the serial modulus and also the damping of the material, as we call it also G gamma D curves, shear modulus, shear strain, damping curves. Here in these diagrams, you can see on the left there are shear modulus versus strain and damping versus strain for sand specimens. Next, we have a new cyclic triaxial device. We have performed many tests, more than 500 tests. It's fully PC digitalized, and all the data or the results are gained via PC. Of course, we use cylindrical specimen. It has many abilities. And of course, there is the option to add bender element tests, which are gonna be more specific later. As you see here in this red circle, this is the main frame. So I'm gonna also show you a closer picture. This is the frame. The soil is inside here, a cylindrical specimen. This is also equipment to calculate, this is the bender element equipment to calculate the VS, VP, as we call them, the shear wave velocity or primary wave velocity of the soil. For cyclic triaxial experiments, now I'm showing you some representative results that we have made in the past. So on the left, you see the these are two types of tests that we perform. On the left, there is the strain control tests, where we can calculate shear modulus or elastic modulus and damping parameters. From these stress-strain loops here, we can go to these diagrams, which are shear modulus and damping versus the strain. On the right, of course, we are able to perform stress-controlled tests in order to be able to define the liquefaction potential. And mostly for granular soils, sand soils, etc. So, of course, in our lab and with our experience, we are able to combine resonant column and cyclic triaxial tests. As you see in these diagrams, we have combined tests for the same material, for a sand material. On the left of the diagram is results from resonant column tests. And on the left and on the right, there is the cyclic triaxial test. Of course, the deduction curves of the shear modulus and the damping increasing with the shear strain. It's a very common picture. Next, bender element tests, a new way to define the shear wave velocity of the primary wave velocity, of course, under confined pressure. It's a non-destructive method. What we do is this is the soil specimen or a rock specimen, whatever we want to test. And we apply different waves, the wave that we want. We have a transmitter and a receiver. And we can apply either S wave or P waves. And it's very easy for us to do it in the same specimen. In the same specimen, that these tips are used also for S and P waves. So it's very adjustable. As you can see here in this picture, this is it's showing like a pulse, and then this green line here is like the receiver of the receiving pulse. As you can see also here in these results, in these tables, in these diagrams, this blue line here is the pulse that we send, and this orange line is the receiving pulse. From our work, we are able to have this to make these profiles like with depth and be able to calculate the VS and the damping with the depth. As you can see here, this is a borehole for more than 500 meters from Poland for an industrial facility in Poland. So let's continue to the shake table experiments. As Dimitris mentioned, this is a new device that we have installed in our lab. As you can see here, is actually small for mostly for academic purposes, and it is uniaxial. Okay, it moves only in one axial, and it has a payload for almost 80. We can adjust it to 100 kilos and perform acceleration up to 1.5 g, as you can see here in the bullets. So I'm not going to stay in the whole details because of the equipment. This is a picture of a closer picture to the shake table in our lab. This is the actuator that moves the table, and now you can see there is a steel plate above the table because we were doing some calibration in the past in order to calibrate the mass and the force. So next I'm gonna show you some work that we do lately in our lab, and mostly I am focused in this kind of work. It's mixtures for gravel and rubber in different sizes, and you can see here in these pictures of angular gravels, and of course we are able to determine all the shear modulus, shear strain damping ratio. We already make the classification for sieve analysis, and also what is the behavior of the material in different confining pressure. So what we're doing now is that we have put these materials in mixtures in different percentages. We have placed them inside a laminar box in the shake table. This is a laminar box with many frames. You can see also here a section of the laminar box. We fully instrumented it with different uniaxial accelerometers, with laser distance sensors, and we applied different kind of tests of excitations like sinusoidal and of course earthquake tests. These are, as you see here in these diagrams, these are some results that we were able to determine shear modulus and damping from these tests. Of course, now the work is still ongoing, so in the future there will be more results published in a journal. That's all for now. For me, these are some references from our work and some standards that we use, of course, when we carry out the experiments. Thank you. There's also my email here and a QR code of our website. And of course, in the end, feel free to ask any questions about our work. So, Maria, that's all for me. I'm giving the floor to you and Stefania.
Thank you, Tassos. Thank you very much. And Stefania, we are ready for your presentation. So if you can share your screen.
Let me try once again.
So I'm going to stop my...
Can you see my screen?
Yes, we can see that.
Thank you. Good afternoon, everyone. I would like also to thank you, Maria, for the presentation and the invitation. My name is Stefania Apostolaki, and I am a PhD candidate in Aristotle University of Thessaloniki. And this presentation is about the recent advances in seismic hazard assessment in Europe. This work has been undertaken by me and Dr. Evi Riga, which is a teaching member in Aristotle University of Thessaloniki. And first, we will begin with the European Seismic Hazard Model developed in 2020, known as ESHM20. And this model forms the basis for our proposal, for our proposed zonation map for the Greek National Annex of the revised Eurocode 8. As you know, Eurocode 8 is the European standard for seismic design. Let's begin with ESHM20. ESHM20 is essentially an update, a major update of the seismic hazard assessment in the Euro-Mediterranean region. It covers the whole Europe and Turkey. It is a successor to a previous model, ESHM13, developed in 2013, and it supports the first European seismic risk model, ESRM20. These models have received funding from the European Union's 2020 Horizon Programme under the SERA project, and in this project, many research teams across Europe collaborated with the Global Earthquake Model Foundation and the European Plate Observing System. Our team in Aristotle University of Thessaloniki, as Dimitris mentioned, has strongly involved in this effort. So the main feature of ESHM20 is that ESHM20 relies in a fully probabilistic framework. It incorporates significantly more earthquake data than previous versions. One of its main strengths is that it is fully harmonized across national borders, and a major objective was to align its outputs with the needs of the revised Eurocode 8 by working closely with the subcommittee of the Committee of Standardization that is responsible for the Eurocode 8. And in 2021, this subcommittee decided to include maps of ESHM20 as an informative annex in the second generation of Eurocode 8. All data, models, and outputs are freely available through the site of FR, shown at the bottom of this slide. Let's see the main results of ESHM20. The main results are more than 500 hazard maps for various intensity measure types, such as the PGA, which is the peak ground acceleration. It is a common metric, and spectral accelerations for various periods, and for 5 mean return periods from 50 to 5,000 years, and for rock conditions. Other results are hazard curves and uniform hazard spectra for every site, so for every location of included in the study area, which is the whole of Europe and Turkey, at a dense computational grid. So we can have this information at every location. Let's see some indicative results. These are maps of the peak ground acceleration, PGA, for a commonly used return period of 475 years. This is a very common return period. This represents the expected levels of PGA for an earthquake that happens roughly once in 500 years. And here we can see hazard curves for 2 selected locations. As an example, for L'Aquila in Italy on the left and Rhodes in Greece on the right. These curves show the annual probability of exceedance for a range of PGA values, and we can have it, as we said, for every location. Now let's move on to how we used these ESHM20 outputs for our proposed zonation map. Let's begin with the current zonation map. This map is included in the Greek National Annex of the current version of the Eurocode 8. It is in force since 2003, and it divides Greece in 3 seismic zones with PGA values of 0.16 G, 0.24 G, and 0.36 G. In the upcoming revision of the Eurocode date, significant changes are expected in the way that the seismic actions are defined. Now the basic parameter will not be the PGA, but we will need 2 other parameters, the S alpha, which is the maximum spectral acceleration, that corresponds to the constant branch of the elastic response spectrum, the plateau value, as we used to say. This value is linked with the PGA by a factor F, capital letter A, which is almost equal to 2.5. So S alpha is PGA, PGA is S alpha divided by 2.5. And the second parameter that we will need is the S beta, which is the spectral acceleration at a vibration period of 1 second. We will use these 2 formulas here for the calculation of the S alpha and S beta. First, we will need the S alpha RP and S beta RP. These parameters will be included in the national annexes of each country, and they will refer to a specific return period, let's say for the 475 years, and for rock conditions. To these parameters, we will apply the soil amplification factors F alpha and F beta, and a topography amplification factor Ft. So the role of ESHM20 in the revision of Eurocode date. ESHM20 will provide maps for these 2 parameters, the S alpha and S beta, for the commonly used return period of 475 years and for rock conditions. These maps will be included in the annex of the main text of the Eurocode date as an informative and acceptable representation of the seismic hazard in Europe. So we have here the S alpha on the left and the S beta on the right for the whole Europe. And these are the same maps when we zoom in on the Greek territory. We have the S alpha on the left and the S beta on the right. We decided to base our zonation on the S alpha values on the left, as this parameter is more crucial and more relevant to our building stock here in Greece. This is a summary of the methodology that we developed. It is a 3-step process where we tested 3 configurations with 3, 4, and 5 seismic zones based on the S alpha values. To create zones from these point values that we saw on the previous slide, we tested many classification methods, and we found out that the most appropriate is the natural breaks developed by Jenks that groups data into classes by minimizing the variance within each class while maximizing the variance between individual classes. At each step, we tested how well the zone average values match the point-specific PGA values. By calculating the ratio shown in the table here in the bottom, and to ensure that the zonation is representative and fair, we calculated this ratio for each location of the 60 major cities in Greece, and we introduced population-based criteria. For example, for big cities with over 500,000 inhabitants, we require this threshold to remain between plus or minus 10%. This iterative process improved the match with the ESHM20 data from the initial 3 to 4 and the last 5 zones, and finally to 5 zones. The last 5 zone map satisfies all the criteria and is therefore our proposed zonation map for the Greek national annex of the revised Eurocode date. You can see the map here. And we calculated for each zone all the parameters needed for the calculation of the elastic response spectra. You can see also the table here. So to sum up, I believe that the most important points to mention are the proposals official submission for potential inclusion in the Greek national annex of the Eurocode date, and the need to consider some practical adjustments if the map is officially adopted. So this is pretty much all from me.
Great. Thank you very much, Stefania.
You're welcome.
And we have the next presentation from Chiara.
Can you see my screen?
Yes, great. We can see that.
Thank you very much, and thank you very much, Maria, for inviting us. My name is Chiara Amendola, and the presentation that I'm going to show now, it's about how to perform a urban scale, but also a large scale risk assessment, including soil structure interaction. This is a work carried out with Professor Dimitris Pitilakis in our research lab. Now, let's start from the beginning and why it is important to include soil structure interaction in the risk assessment. As you can see from these pictures that I put here, these are pictures taken from the recent central earthquake sequence in Italy and from the earthquake in Turkey. And as you can see, these are evidence of soil structure interaction because because of the interaction with the foundation subsoil, you can see a tilt, a rocking of the structure, and also here with these magenta arrows, an uplift of the facade. But what is the problem? The problem is that in general, these, let's say, large-scale risk assessment are performed considering literature fragility function. These means that these, let's say, fragility function are generally carried out considering the structure fixed at its base, so neglecting soil structure interaction. So for this reason, we propose a method to include such effects in the urban scale risk assessment. The method that we propose, it is of course in line with the general framework for risk assessment. So of course, we need to define the seismic hazard, but we will have also to define the exposure model. Now, the exposure model, since we need to account for the presence of the foundation and the interaction with the foundation subsoil, we need to modify it to include, let's say, a proxy of the foundation that can be, for example, the building footprint area that it's available, let me say, a global scale, and the proxy for the soil condition that can be, for example, the VS30 that again is available at a global scale. Then we need the fragility or vulnerability function, and this vulnerability function, of course, they need to be developed considering soil structure interaction. For this reason, what we have done is to compute fragility function considering single degree of freedom system, and now we updated this to multi-degree of freedom system. Once, let's say, considering soil structure interaction, so with the system of springs at the base, and once considering the general approach that is the fixed base assumption. In this way, we can end up with the two sets of curves, the fixed base that here are the continuous line, and the flexible base that in this case are the dashed ones. As you can see, for example, here there is an increase of the fragility because the dashed curve is on the left-hand side. General, when we account for soil structure interaction, depending on the kind of structure, but especially even the fundamental period of the structure in relation to the dynamic characteristic of the input motion, the property of the soil, the characteristic of, let's say, the foundation, and more in general, the interacting system, you can have an increase or a decrease of the fragility function with respect to the fixed base assumption. In this case, for example, especially for this tall building, when we consider soil structure interaction, we have an increase of the fragility. This is a case of a very soft soil profile, because here the soil, it has a VS30 of 150 meter per second. We say that we have to also modify, let's say, what is the general exposure model. And to do this, we provide in our GitHub page, let's say, the tools to modify the exposure model in order to account also for the foundation and for the soil. Now let's see an example of this methodological framework applied to compute the damages in Thessaloniki for this event, the magnitude 6.5 1978 earthquake. Here you can see some pictures taken from this historical earthquake that in particular caused the collapse of a building in the city center. Now, just to have some information about let's say the characteristic of the case study, on the left-hand side you can see the distribution of VS30 within the city, and just a focus on the fact that on the coastal line, so close to the sea, we have the softer soil profile, while on the right we can see the ground motion field on rock. Computed with the OpenQuake software, and as you can see, the largest intensity measure are, let's say, towards the epicenter. Now, if for this event we compute the damages for the two cases, so on the left considering the fixed base assumption and on the right considering soil structure interaction, you can see that first of all, there is a different distribution of damages. These dots represent the percentage of number of buildings, for example, here in the slight damage state, in the next slide in the complete damage state, and just to highlight that, for example, if we see what happens on the coast for the fixed base on rock assumption, we will see less buildings experiencing this complete damage state, while if we consider soil structure interaction, the number will increase. All in all, we can see that we can also aggregate these results, and even from this pie chart, you can see that the distribution is different. If again we focus on the case here on the coastal line in the region, in the district of Kalamaria, you can see that the pie chart from the left and the right hand side, it will change. Here there is an increase in general of buildings in the higher damage state. And again, if we aggregate everything to see what happens at the city level, when we consider for this application, so for the historical earthquake in Thessaloniki, when we consider soil structure interaction, we will have an increase of the percentage of buildings, for example, experiencing the complete damage state. Now, another important thing to understand the results related to the case study is that if we aggregate the damages in terms of the VS30 where the building it is resting, we can see that for all the buildings that stay, let's say, on a soil profile with a velocity of about 180, so very soft soil profile, there is an increase of the probability of having higher damage states. So in this case, we have an increase of the damages. And just to conclude this presentation, in general, when we perform this kind of analysis, in order to check also the results, we try to compare with the real damage collected if they are available after an earthquake. And we have done this for this historical earthquake, considering that, as you can see here in this slide, the higher part of the city, that is called Danopoli, that is highlighted in orange, it is mainly constituted by masonry structure. And in particular, there is one typology, a low-rise and confined masonry structure, that it was the most heavily damaged during this historical earthquake. So we compared the damages collected after the earthquake by the engineers, that basically they were accessing the buildings and they were giving a tag color, so green, yellow, or red, depending if it was accessible, usable, or it needed strengthening before accessing the building, or if it was completely, let's say, unsafe to go there. And we compared the results with this earthquake post-tagging, as it is called, with the damages that we obtained from our analysis. And in particular, these are the results for this case study masonry structure that it was the most heavily damaged, among the most heavily damaged within this earthquake. And we can see that the distribution of damages compares very well when we consider soil structure interaction, while it is slightly different. It is different when we consider the approximation of the fixed base structure. So with this, I would like to thank you again for attending this presentation. And if you have any question, and here I put some references that maybe can be helpful. I will stop sharing.
Thank you very much, Chiara.
Thank you, Maria.
Thank you all for the presentations. And now I will open the floor to questions. So anyone of the audience, if you have any question, you can either unmute yourself or otherwise you can type the question in the chat. So let's start with Mohammed.
Yes, hello. Thank you very much for the presentations. I have a question for Tassos on the
Yes, of
low-cost seismic isolation. Is there any specific reason why you limited the gravel to rubber to 70 and 30%, since it seems you're getting good performance in terms of low acceleration and larger damping as the rubber content is higher?
Okay, let's define that. First, we had performed some experiments on the field on Eurosize test. I don't know when Dimitris made a presentation about that. We used these percentages, 70-30. So with that percentage, the behavior of the mixture is like a rubber-like behavior, like more elastic, more linear behavior, even in high strain conditions. That's why we chose to keep that this percentage.
How would your results differ if, let's say, you went for a higher 40% rubber or 50% instead of 30%? Would there still be significant benefits, or it wouldn't change much? And
there is, I think, like there is a point. There is a point when the behavior of the material is totally rubber-like, like it changes, like snaps, like differently. So even like if we add more and more rubber, the connection of the rubber, like the more and more grains of rubber are touching, and the gravel is not making any difference. Like it's mostly like rubber. Actually, and also, as I've seen, like the results, and from my experience, like it's if it's more than 70-30, then the behavior changes a little.
Okay, and also you lose shear strength. You lose when you add more rubber. So you want an optimum.
Yeah. We are trying to balance things.
Yes. Okay. Thank you.
You're welcome.
We also have a question by Marco for Chiara. So the question is, how do you determine the parameters for your analysis? Is there any software helping with it?
I think maybe it refers to the parameters to define, let's say, the building and the foundation and the soil. If so, can I see the question? Yes, maybe yes. In the chat. Yes. Chat. Okay. Yes. No, we didn't use a software in defining the parameters. We kind of, let's say, we did, and it was actually one of the slides that I presented. We wrote a routine in order to, for example, to determine automatically from the, I don't know, from the OpenStreetMap, the foundation footprint area, just to have, let's say, a proxy for this information. And then we converted this in for example, in the structural height over the foundation width ratio in order to then determine the foundation parameters. While all the other parameters such as the soil, all the soil parameters more or less are available, but more specific parameters in order to define, for example, the non-linearity of the foundation, these are based on the literature studies. So we did, let's say, a study for this. And also we also checked, for example, in the case of Thessaloniki, what was according to the year of construction, the typical, let's say, foundation dimension. So we did a kind of a study for this.
Okay, thank you. Thank you.
Thanks.
Okay, great. We don't have any more time for questions, so we need to close the presentation. Maybe would that be okay if the speakers would be contacted by anyone who has more questions? We can take one last question as I see someone, and then if anyone has any more questions, you can contact the speakers through email, if that's okay.
Yeah,
Okay,
that's
so
fine.
let's have
Yes.
let's have the last question. If you could unmute yourself, please. Hello, can you hear us? Okay, so I
he
see the
wrote it in
question
the
written.
chat.
Yeah,
Dimitris?
if it is possible to visit
Yes, of course you can
Europroteas.
visit Europroteas. Definitely, we will be more than happy to welcome you there.
Okay, great. So I guess you can contact the speakers directly, and that can also be arranged, or any other question you may have. Thank you again, Dimitris, Tassos, Stefania, and Chiara, for presenting the lab activities and research, and giving us some case studies in Thessaloniki, as well as virtually guiding us in the lab and the field facility Europroteas. Thank you everyone for attending, and this will be available on our YouTube channel.
Thank you.
Have a good day.
Thank you, Maria. Thank you all.
Thank you, Maria.